Ladies and gentlemen, welcome. This is again our seminar 4ST441, Statistical Methods and Capital Markets. The number of seminar is 9, our 9th seminar. And if you remember, last week we started to speak about volatility models. Yes? About the modeling of volatility, and the first type of model designed on modeling of volatility, of changing variability, changing variance in time, yes, was autoregressive conditional heteroscedasticity model. Yes, we started to speak about conditional heteroscedasticity. And because the data was modeled in squares, in square values, we had to speak about this conditional heteroscedasticity, about the changing of variance in the time. If you remember, I showed to you only autoregressive conditional heteroscedasticity model with order p equal to 1. Yes, if you remember, when we speak about ARMA structures, we talked about autoregressive models and moving averages models separately, and autoregressive models used the order p, moving averages used the order q, yes, p equal to something, q equal to something, yes. And here, because this is conditional heteroscedasticity modeled by autoregressive process, we are also using the order denoted by p. So, in general, we will speak about models of order p. As I already said, Arch1 model is not satisfactory since it's not capable of properly capturing the volatility dynamics observed in real life. Yes, sometimes it's necessary to use more lux. Yes, more locked values. Not only the value in time t minus 1, but more lux t minus 2, t minus 3, and in general t minus p. So-called P models could be employed instead. Yes, their conditional variance ht is defined as this following formula. Ht is equal to omega plus alpha 1 logarithms squared in time t minus 1 plus alpha 2 times logarithms r squared in time t minus 2 plus etc. And finally alpha p times logarithms r squared in time t minus p. Yes, so the p number, yes, of the lux. However, a large number of parameters of an RP model is required to capture the volatility dynamics properly. Yes, there are two important things. Yes, it's good to use a lot of lux. Yes, for the properly, yes, capture of the volatility of the dynamics, but it's necessary to have most parameters statistically significant. Yes, the model with many parameters which are not significant is a wrong model. And if you remember, when we talked about, for example, information criteria, Schwarz information criterion and Hannan-Quinn information criterion, yes, these criteria increase, yes, very strong increase if you have in the model a lot of parameters which are not statistically significant at 5% significance level, yes? So it's good to use a lot of lux, yes, but it's necessary to have most parameters statistically significant, yes? So two important things which are in the cross, yes? Okay. You remember, yes, one illustration from previous week, from our previous seminar. We used Gaussian white noise process and we tried to model, we tried to generate some process. And today we also use Gaussian white noise process, yes, and in the case of exercise 30, we will do this. Let us assume the following model for logarithms, yes, imaginary logarithms, yes, so RT is equal to HT powered by 1 divided by 2 times ET. It's necessary to note that HT powered by 1 divided by 2 is a square root from HT, square root. The power function and 1 divided by 2 is square root from this. So RT logarithms are equal to square root from HT times ET, where ET is Gaussian white noise process with unit variance, and according to this following formula, we will generate HT. Yes, HT will be equal small constant, as for example, small. If I scroll back, you can see here HT omega. Yes, so small omega, for example, only 0.001 plus 0.5 times t squared in time t minus 1 plus 0.3 t squared in time t minus 2. Yes? So, in comparison of previous week, there will be one more term. Yes? Model RP model, for example, in use or other software. So in the first step, it will be necessary to generate the process in Excel, for example, or other software where you are able to generate some processes according to your conditions. Yes? And after, we will use this process, for example, in your software, and we will try to find a model, yes, according to estimation of equation. Okay, so I opened for you a Gaussian white noise process which we already generated in the past, yes, many weeks ago. So here we have a column with 500 values of the Gaussian white noise process, and according to slide which you could see 1 minute ago, yes, it's necessary according to time variable t, yes, according to time variable t, generate the conditional variance, yes, the conditional variance HT. So we have here the linear development of the time variable t, and next to this time variable t we have prepared HT, where we create the conditional variance. Yes. So on the first position here, because we don't know the previous value of time t and the previous value of time t minus 2, there will be only equal sign 0.001. Yes, 0.001, the constant, the omega, yes, the intercept. Okay, enter. So this is the first observation. On the next observation, we already know the previous value of time variable t. So we will write here equal sign 0.001 d omega, yes, plus parameter 0.5, yes, we set the parameter 0.5 times the previous value of time variable t in squares. So we must use the hat, and this will be squared, yes, the second power. Okay, so this is second observation, yes, of the conditional variance HT. So we can click enter, and there will be the universal, the general formula, which will be copied to the end. So we will write here the third observation, equal sign 0.001 d omega plus 0.5 times the previous value of t squared, yes, we will write the hat squared plus 0.3 times the time variable t on observation t minus 2 but in squares. So we will write here again the hat powered by 2. Okay, so this is the universal, the general formula of this conditional variance, which will be copied to the end. So please copy the formulas to the end, and this is the conditional variance HT. And on the basis of the conditional variance HT, we will generate the log returns in time t. So we can start right here. There is HT powered by 1 divided by 2. Yeah, so this is the square root from the conditional variance. Yes, HT powered by 1 divided by 2. Okay, times the Gaussian white noise process, the value of the Gaussian white noise process on the row where we are placed. Yes. Okay, and this is universal. We can copy this to the end, and we have the log returns. Yes, so perfect. There we have the log returns, and we will prepare the space. We will prepare the space in eViews software. So please open eViews. I have an empty window in eViews software, and we will open the work file, and we will generate a file for this time series of log returns. So please, we will click on File button. We will use New. And there we have a new work file. Yes. So work file frequency, we will set integer date, start date 1 and end date 500. Yes. The space for 500 observations. So we can click on OK, and there in this window we will create the file. We'll create here a file, for example, RT, like log returns. So in the command log we will write the command series space, for example, RT, yes, RT equal to 0. Enter, and here you can see prepared a file for the data. We will click on edit plus minus, and this file is unlocked. Yes, and we can copy here values from Excel, but without formulas and with dots instead of comma. So in our Excel we will use copy, as we will select all values. We will use copy, Ctrl C, and we will use paste values. Yes, paste values 1, 2, 3, paste values, and we deleted the formulas. We will use the shortcut Ctrl H, find and replace. Yes, and we will find commas. and we will replace by dots, yes, and we will use replace all, and you will see that we replaced 500 items. Okay, you have here 500 values. So without label, only the values, 500 values, copy, Ctrl C, and please paste to eViews here. So we have here the values, and we can use the view button, and we can check the chart, we can check the graph, what we created. Yes. So there is the development of our logarithms of our time series. Yes, you can see increasing volatility in time. Yes, increasing variance in time. Yes. So according to our slide, yes, we will try to model this prepared time series of logarithms by autoregressive conditional heteroscedasticity model with order equal to p. Yes, we don't know. We will start, for example, with p equal to 2. Yes, because on our previous seminar we created arc model with p with order equal to 1 only. Yes, and today, because we generated conditional variance with omega and 2 parameters. We'll try to estimate arc model with p equal to 2. So we can leave this here, and we can click on quick button, yes, quick, estimate equation, and here we will write dependent variable, yes, arc model, autoregressive conditional heteroscedasticity model, using a dependent variable in squares. So we will write here RT hat, and second power, yes. Okay, so this will be our dependent variable. We can write here, for example, constant. We will start with constant, yes, and we will write here RT in parenthesis -1, RT in parenthesis -1 hat square, because this must be also in squares, yes, okay, space, and RT in parenthesis -2, the second log, but in square, so hat squared. Okay, so it's not necessary to click on options because there is no autoregressive process. Yeah? This is simple regression. So it's estimated by least squares method. We can click on OK, and we will see the results. Yes. We can see that the intercept, the constant, is statistically significant. The first log, RT in the first log squared, is statistically significant, and RT in the second log squared is also statistically significant. Yes. Where is written Darby-Watson statistic 2.04? Yes, 2.04. We will check the residual diagnostic, but we'll check the residual series before the residual diagnostic. Yes, if the constant is necessary, it's significant. Yes, but we'll check if this constant is necessary in this model. Please click on View button. Yes, and we have here actual fitted residual, and please check actual fitted residual graph. Yes, okay, you can see that our fitted values are above actual values because of constant. Yes. If you check this chart, yes, where you can see that the conditional mean, yes, is probably equal to 0 or very close to 0, in our situation, constant is statistically significant, but maybe will be better if the constant will be omitted from this model. We will omit constant. Please click on estimate. Zoom this, and delete the constant. Yes, we will omit the constant from the model, and we'll click on OK. Yes, perfect. So there is one coefficient 0.22, second coefficient 0.73, both statistically significant. Darwin-Watson statistic 2.0999, and we will check the residual series. Please click on View, actual fitted residual graph, and now you can see, yes, that the green curve, yes, is more similar to the red curve. Yes, here actual and fitted are more close. Okay, we will try to increase the number of parameters because we don't know the finite number, the concrete number of locks. Yes, we set p equal to 2, but we don't know if this is alright or not. Yes. Yes, we can use, for example, we can use the tool autocorrelation function. Yes. So it's possible. Please click on View button. And find here residual diagnostics, correlogram Q statistics, okay, and there we have the correlation structure. Zero hypothesis. There is no correlation. Yes, there is no system. This hypothesis is rejected. The 5% significance level. Yes, so probably p equal to 2. Yes, 2 lux. In the case of this ARC model, autoregressive conditional heteroscedasticity model is not enough. Yes. Darwin-Watson is 2.1, yeah, very close to 2, so probably there is no correlation, autocorrelation according to Darwin-Watson statistics, but according to Leung and Box statistic, there is autocorrelation. So it's necessary to increase the number of lux. So we will do this. Please click on estimate. Yes, zoom this equation and write here RT in parenthesis minus 3, hat and second power. Yes, so we will add one more coefficient, yes, one more log. We can click on OK and we must check the result. Yes, you can see first coefficient 0.17 statistically significant, 0.30 second coefficient statistically significant, 0.15 the third coefficient statistically significant. So all three coefficients are statistically significant. We can check Darwin-Watson statistic. 2.03 is a little bit smaller. Than before, and because we tried to increase the model, and I don't know where is the end. I don't know where is the final lock which will be put to this model. It will be good to remember or copy information criterion. Yes, so we can copy this, Control C, as for example formatted, okay, and I don't go for example to Excel. Yes, we can open Excel and here next to these columns we can copy these criterion. Perfect. Yes, so this is our model with 3 lux. Yes, this is our model with 3 lux. Because we will try to increase the number of lux. Yes, one more time or 2 more times, etc. Because we don't know where is the end. Yes, so there we have 26 point something, 26.55, 58, 4ST441, yes, according to Akaike, Schwarz and Hanan Quinn. We'll return to reviews and we will check the residual series. Please click on View, Actual Fitted Residual Graph. Yes. There is probably no significant difference. Yes. According to our eyes, we are not able to see something interesting. So we will check, for example, Ljungbox Q statistics. Yes. Because we need to explain the variability, yes, the dependence. So please click on View button, Residual Diagnostics, and we will set Corellogram Q statistics, Ljungbox Q statistics. Okay, and there is a better result than before, yes. Zero hypothesis. There is no autocorrelation. There is no autocorrelation. Is not rejected in case of first luck. Yes, in case of first example here, first value. Yes, so this is really better situation because in the previous case where we had the arc model of order 2, we had autocorrelation. Now, we don't have autocorrelation of the first order, yes, of the first order only. So, we will try to increase this model one more time. So, we will click on Estimate, we will zoom this equation, and we will add here, space, RT log returns minus 4, yes, on the fourth log, hat to second power, yes? So one more coefficient, one more log. So we can click on OK, and you can see there is the first coefficient, second, third, and fourth, 0.15, 0.27, 0.14, and 0.10. All statistically significant. Also this one is statistically significant at the 5% significance level. Darby-Watson statistic 2.05, very close to 2, but we know that it's necessary to check the residual series, yes, residual time series, and diagnostic test. Mainly Ljungbox Q test for autocorrelation. So again, please click on View button, Actual Fitted Residual and Actual Fitted Residual Graph. Again, there is probably the same development of residuals. So we will click on View, Residual Diagnostic, Corellogram Q Statistics, and okay. And now you can see that we don't have autocorrelation of the first order and we don't have autocorrelation of the second order. Yes, so this is again the better situation in comparison with previous example. Better. If this is really better, we expect that we have smaller values of information criteria. Please return here View Estimation Output, Akaike Schwarz Hanan Quinn, copy, and open, yes, formatted, open Gaussian white noise processor Excel, and we can compare this. It's a very, very small difference. 26.557, 26.553. Yes, there we have 26.582. There is a little bit higher value than before because Schwarz criterion is designed differently, yes, than Akaike, for example, criterion, yes, and there we have Hanan Quinn 26.567, there is Hanan Quinn 26.566. So in the case of two information criteria, and there is again lower. In the case of two information criteria, Akaike and Hanan Quinn, we have lower values in the case of 4 lakhs, yes, and in the case of Schwarz criterion, there we have a little bit higher. So you can see that in the case of information criteria, we have very, very small differences, yes, and you can see that the design of these criteria is different. So in the case of Bayesian information criterion, yes, there is a higher value in the case of 4 lakhs, yes. So the final decision depends on us, yes, on statisticians. We know that autocorrelation, the situation about autocorrelation is better in the case of 4 lakhs, yes. Two information criteria are lower in the case of 4 lakhs, yes. So we can prefer that it will be better to use 4 lakhs. I prepared this example for you in advance, so I know that if we use 5 lakhs, yes, we will have statistically non-significant coefficients. But I will show this to you, yes. So here is our model where we have auto-regressive conditional heteroscedasticity model with p equal to 4. Please try to click on estimate. We can zoom this equation and we can add here RT in -5, yes, on the 5th lakh, hat 2, yes, and we can click on OK, and now you will see that the situation changed, yes. There we have now non-significant values as of RT in time t minus 3 and RT in time t minus 4, yes. So these coefficients are not significant. The Darby-Watson statistic is 2.05, so very close to the value which we had before. We have here again the almost similar values of information criteria, 26 point something, yes, 26.49, 26.53, 26.50, yes. And we can check, for example, the correlation structure. We can click on View button, Residual Diagnostics, Correlogram Q Statistics, okay. You can see, as you can see, that now there is better situation in the case of autocorrelation, yes, but we don't have statistically significant coefficients, yes. So you can see very interesting situation, but real in the real life, in the real world, in real economy, yes, that we are trying to add more and more parameters, yes, and we have better results on one side, better results of autocorrelation, better exploring of correlation structure, but the price is that we don't have significant coefficients, yes. So for us, for statisticians, it's necessary to explain enough variability with the model with the most of significant coefficients, yes. It's not optimal to use model with coefficients which are not statistically significant, yes. So our recommendation in this case is to use ARC model with p equal to 4. Autoregressive conditional heteroscedasticity model of the 4th order. We will continue with speaking about regressive conditional heteroscedasticity, but now in general, yes, there exists generalized autoregressive conditional heteroscedasticity models, yes, which are denoted by letters GAR, yes, generalized autoregressive conditional heteroscedasticity with parameters, yes, with some orders, parameters and orders. So a GAR 1-1 model of order 1 and 1, where P is equal to 1 and Q is equal to 1, yes, is the first situation, the first and the basic situation of the generalized autoregressive conditional heteroscedasticity model. And for logarithms or other variables, yes, is given as, you can see that this is the same, yes, in the case of generalized autoregressive conditional heteroscedasticity models. Logarithms in time t are equal to ht powered by 1 divided by 2. What is the square root from ht, yes, times et, where et is often assumed to be Gaussian white noise process with unit variance, yes. So, very important from this slide is that the shortcut GAR means this, and the numbers, yes, in the parentheses, numbers in parentheses, are orders of this GAR model, where the first number is P and the second number is Q, yes, and this is very, very closely connected with ARMA models, where we also use parameters P, or orders of this model P and orders of this model Q. Yes, so RT is equal to this formula, and HT is time varying conditional variance for time t given s. So please read this formula. We can see that HT is equal to omega, yes, some intercept, some constant, yes, plus alpha 1 r squared in time t minus 1 plus beta 1 h in time t minus 1. So, very important, please check this formula. You can see constant, the intercept, yes, omega is the parameter of this model. Alpha 1 r squared in time t minus 1 is again, alpha 1 is again parameter, and there you can find, yes, you can find the part from our model where we are using second power of logarithms, yes, second power of logarithms in time t minus 1. Then you have beta 1, so another parameter, yes, so omega, alpha 1 and beta 1 are parameters, yes, this is constant, parameter, and here there is variable logarithms in squares, yes, and there is variable h in time t minus 1 without squares, yes, without squares. The identification is similar to that of RP, yes, with the exception that we are adding moving average terms, yes, moving average terms. So this first part, yes, is similar to our model, and we edit a moving average term. If alpha 1 plus beta 1 is smaller than 1, logarithms, the series of logarithms is stationary. Yes? This is condition, and in the case of model, if you see the result, yes, from regression analysis, and if you calculate the summation alpha 1 and beta 1, and the result is smaller than 1, logarithms are stationary. Okay, so we can continue with other practical exercise. Exercise 31. Let us assume that following model for logarithms RT logarithms are equal to HT powered by 1 divided by 2. So again, our well-known square root from HT times ET, where ET is Gaussian white noise with unit variance, and we have here the following formula for the conditional variance HT. HT is equal to, for example, 0.2 omega, yes, plus 0.5 times t squared in time t minus 1 plus 0.3 h in time t minus 1. Yes. So there is the first part where t is in squares. There is a second part where we have h without squares in time t minus 1. We'll try to model the GARH P model in, for example, eViews, or we can use other software. Yes. So again, it will be necessary to generate. Yes, it will be necessary to generate the process. The process, for example, in Microsoft Excel, and after we'll try to find the model in eViews software. Okay, so there is our well-known file, the sample with our Gaussian white noise process, and according to formula from our previous slide, we will create a new process of the conditional variance. Yes, conditional variance HT, which is written here, prepared here. The formula was 0.2 plus 0.5 t squared in time t minus 1 plus 0.3 h in time t minus 1. Yes, but because we don't have already value t in the previous observation and value h in the previous observation, yes, on the first position there will be only the constant d omega, yes, from our formula, so the value 0.2, so there will be only equal sign 0.2 enter, yes, nothing more. On the next position we already have previous value of the time and the previous value of the conditional variance. So we will write 0.2, the constant d omega, plus 0.5 times previous value of the time squared. Yeah? So this value f2 must be in square, so we will use the hat power function 2. Okay, so there is second power of previous value of the time plus 0.3 times previous value of ht, so this value. Okay, and this should be the end, yes, because this is our formula of the conditional variance. So we will copy this formula to the end. Yes, okay, so there is the development. And RT logarithms will be calculated in the same way like before, like in all our previous examples about logarithms. So there will be equal sign. We will use HT, the conditional variance, powered by 1 divided by 2, so power function, in parentheses 1 divided by 2, so this will be again the square root, yes, this will be the square root from the variance, times Gaussian white noise process, the value of the Gaussian white noise process from the row where we are placed, yes. Okay, so there we have first value of log return. We will copy these values, these formulas to the end. Yes, and there we have a development of log returns. Yes. Okay, now it will be necessary to put these values to eViews software. I have already prepared eViews here. So again, we'll click on File button. We will click on New Work File because we need a work file with 500 observations. Our frequency will be integer date, and start date will be 1, and date will be 500. Okay. There will be a work file with 500 observations, and in the same way like before, we will create here a file. So we will write here, for example, series. The name will be RT space gar. Yes, for example, RT, yes, space gars equal to 0. And we have here a sample of a file with 0 values, 500 0 values. So we can open this. As you can see, we have here 500 0 values. We will click on Edit button, Edit plus minus, and we are able to paste here the generated values from Excel. But we must delete the formulas and instead of commas, put dots. Yes, so we will select 500 values here. We will use copy and paste values. Yes, paste values only. So we deleted the formulas. Now we will use the shortcut Control H. Yes, so we will select again 500 values. Control H, find and replace. We will find the comma, and we will replace with dot, and we will click on replace all. Replace all, and you will see the message that everything is done. We replaced 500 items. Yes, so okay, and this can be copy and paste to eViews. So again, we will select 500 values, copy, and in eViews from the beginning we will use Ctrl V, paste. Yes, and there we have a development of some generated log returns. So we can click on View button. Yes, we can click on Graph, and we'll use light and symbol. Okay. And there is the development. There is the development of our log returns. Yes. Again, you can see that the development seems to be similar to our previous development of log returns, which were generated in the previous example. Yes. It's logical, because according to structure of the formula, yes, we need to see the increasing volatility, increasing development of amplitude of this distribution of this time series, yes, of log return. So there we have our sample size, and I said that I'll show to you how to estimate GARC model in eViews. Yes, it's not easy, so I'll show this to you like illustration, and after I will show to you again illustration of ARC model. So where can we find the estimation of GARC model in eViews? It's not such easy like in the case of model ARC, because the ARC model we were able to model only in equation specification. Yes, it was classical regression model where we used the squares only. Yes, only one exception was that we used squared values instead of original values. Yeah? Dependent variable was in squares. Independent variables in lakhs, yes, were in squares. So this was easy because we could use classical quick and estimate equation. Now we will use again quick estimate equation, but here in estimation settings we have a method least squares. Yes, classical least squares method, yes, could be used for classical arc model, but now we would like to use GARH. And there you can find arc autoregressive conditional heteroscedasticity. But this method, yes, this special method is prepared mainly for generalized autoregressive conditional heteroscedasticity models. So please select this arc method for estimation. And you can see that there is a little bit different window for different specification. Very important. In our work file, we have RT-GARH, yes? And in the case of classical autoregressive conditional heteroscedasticity models, yes, this variable was modeled in squares. So we used RT power function and 2, yes, RT with hat. Here in this specification we will write RT-GARH only without squares, yes, RT-GARH without squares. Because this procedure knows that we need to model arc or GARH, yes? You can see that there is no arc. There is only general autoregressive conditional heteroscedasticity or threshold autoregressive conditional heteroscedasticity. Yes, so we will leave here this GARH model. You can see orders. Parameter arc P equal to 1, parameter GARH Q equal to 1. We are able to set here the parameters, the order of parameter P and the order of parameter Q. Yes. Okay, so this is possible. It's possible to use constant here or not. Yes, I don't know if it's necessary to use constant or not. So we will write here the constant, yes, and we will try to estimate this. Yes, maybe it will be necessary to remove this constant. I don't know. Yes, so this is illustration of estimation of GARH in eViews. So please click on OK and we will check what is written here. Okay, so dependent variable RT-GARH, as this model knows. This procedure knows that we need to model this variable in GARH process. Yes, so it was not necessary to write here second power, etc. Yes, what else is important here? This formula. Yes, this formula written here. But before I will comment what is written here. This constant, this variable C, which is written here, 0.90, is not statistically significant at the 5% significance level. This is our constant, which was placed as to the model in our estimation procedure one step before. Yeah? So, because this coefficient is not statistically significant, this is probably because our time series oscillate around 0. Yes, probably. So we will omit this constant and we will estimate only this part about variance equation. Yes, there is a part where we have c or other variables, yes, put it to the model, but in the estimation of GAR, there is the most important estimation of the conditional variance. And the conditional variance is written here, so we will omit this coefficient c, this constant, so we can return on estimate there where you can see RT-GAR, yes, and c, so this c will be deleted. Everything else is the same, so you can click on OK, and you will see that this C is omitted now, and there is only the formula of the variance, of the conditional variance. Yes, the main issue, yes, in the case of GAR model, is estimation of the variance. Estimation, exploring, yes, and description of the variance in the data set, yes, and our omega, yes, so there is universal formula of the conditional variance where we have here c, the constant, some estimated omega, yes, and two parameters of model GAR, where you can see residuum in the first log squared. So this is connected with our time squared as variable, and GAR minus 1, there is the part connected with the moving averages. So according to our slide, which was written, which you could see before, we have here alpha and beta parameters, yes, of the estimated formula of variance, and we can see that there is value 0.04 and 0.97. If we calculate the summation of these coefficients, alpha and beta, we have value very close to 1, yes. 0.97 and 0.04 is 1.01, yes. And I have here the presentation, and we can return one slide before. If alpha 1 and beta 1 is smaller than 1, RT is stationary. I believe that we have stationary logarithms, because you could see that the values oscillated around 0, yes? There is probably no possible option to be non-stationary. Yes? So I believe that at 5% significance level, yes, this alpha and beta, yes, is it should be smaller than 1. Maybe there is some systematical error. In our data. You remember that I wanted to show you before ARMA process, yes, where we generated very nice ARMA process in eViews in Excel and copied the values to eViews, and we didn't have a significant coefficients, significant parameters, yes. So it should be stationary, yes. I don't know why now, as we have the value alpha and beta a little bit higher than 1.01, as both coefficients statistically significant. So we can return to eViews as here statistically significant, but this is the estimation of the conditional variance, yes, for this Garch model. You can see that it's not easy. If you download, for example, the real data set, yes, the real data set from internet, from, for example, Yahoo Finance, yes, you can calculate on the basis of our well-known formula, the log returns from prices, from stock prices, yes, log returns from stock prices. You can put this time series to EUs, and you can try to estimate this Garch model where the result, the main result of this model, this formula of conditional variance, yes, which is here, and you can compare your values, the real values of coefficient alpha and beta, as omega is not important for us, yes. Omega is here just like omega, just constant, but alpha and beta, yes. Alpha and beta talk about the stationarity or non-stationarity. We can try to use here in this formula, in this development of time series, we can try to test this. Please click on view button. We have here unit root test, yes, unit root. Yes, of course, level known. We will start with known. We will start with the first version of Dickey-Fuller test. We know that zero hypothesis is non-stationarity. Yes, zero hypothesis, non-stationarity. This hypothesis is rejected. Yes, it should be stationary, and because zero hypothesis is rejected, yes, alternative hypothesis claims that coefficient rho is negative. Yes, rho is smaller than 0. You can see that coefficient rho is here, minus 1.01, minus 1.02, and this coefficient is statistically significant. Yes, so there we have two information, yes, in the cross, but it's real. Yes, this happens in the real life, in the real data set, not only in simulated data sets, but of course in the real data sets. And because you can see that this is difficult, yes, at the end of our example, we will model our data set by classical arc process, which is easy, more comfortable for us, and I think that it's sufficient for this course. For our analysis, it's sufficient because we clearly understand to arc model. So we can close this, yes, we can close this window, it's not necessary for us. We can close this as well, yes, delete, yes. There is our time series, and we will click on quick button. We have here estimation equation and our classical dependent variable log returns Garch squared. Yes, so we will use the hat squared. Okay, I will not use constant because we believe the constant will not be statistically significant at a 5% significance level. So we will write here RT Garch in -1 hat and 2 because everything must be in squares. And we will write here the same 1, 2, 3 more times, yes, but in the case of second luck, third luck, and fourth luck. Yes, so please write it here. Yes, -2, one more time, -3, and one more time, -4. Yes, there is a mistake here. So there is -4, there is -3. Okay, so this will be arc model of order 4. If anything will be statistically not significant, it will be omitted. So I hope that we have written everything all right. We can click on OK. and we will check the results. Okay, everything is statistically significant, yes? Everything is statistically significant, so the first, second, third, fourth coefficient, arc model of the fourth order, you can check at home if you add more lux, if this will not be or will be statistically significant. Yes, I don't know. This was just experiment because in the previous example we also tried to model arc4. Yes, so you can train at home evaluation of this model, etc. Yes, so the main illustration was show you how estimate GARC in EViews, how to reach the formula for the variance, for the conditional variance, and because it's not easy, we also calculated classical arc model, which is more comfortable for us, and as I already said, it's sufficient for our analysis. We will continue about GARC models, yes, about speaking of GARC models, and now in general, yes. So we know that GARC means generalized autoregressive conditional model, but in the previous cases, as we used only example where P was equal to 1 and Q was equal to 1. Yes? So we used some number of parameters, some set order, yes, of this model. So the GARC11 model can be generalized. So general autoregressive conditional heteroscedasticity model with parameter P equal to 1 and Q equal to 1 can be generalized to GARC PQ model, that is a model with additional log terms. Yes, we can add more logs, yes, to this model. Either in the first part where we have autoregressive part, or in the second part where we have the moving average part, the moving average terms. Yes. Such higher order models are often useful when a long span of data is used, like several decades daily data or a year of hourly data. Yes, in the situation of real data sets, yes, in real economy and in the real world, where we have, for example, high frequency data with a lot of observation, thousands, 10,000s, 100,000 observation. Yes, it's possible to have such number of observation. Yes, it's good to use more orders, more logs. Yes, with additional logs, such models allow both fast and slow decay of information. Yes, there are the same conditions like before, as the memory inside this model decreased by geometrical series. Yes, the most power, the most strength, the most information, yes, is hidden, yes, in the data which are on the position t-1, yes, t-2, t-3, and after the amount of memory decreased by geometrical series, yes, to 0. So again, it's necessary to use statistical testing of parameters, because if you use a lot of lux, yes, 10 lux, 12 lux, 15 lux, 20 lux, etc., yes, you can reach the model, yes, which explains data very well, but most of parameters are not statistically significant, and you have large values of penalization criteria, Schwarz-Quinn, etc., yes, and other diagnostic tests, for example, yes, and this model is wrong, because you are using a lot of parameters which are not significant. Yeah? So again, there we have two issues between the optimal number of observations, yes, and between explained variability, sufficient number of information criteria, and fulfill the diagnostic tests. Yes? So again, the same problems like we had before. Okay, we can again speak about our model, and now for the situation arc infinity. Yes, arc infinity model. This model for HT, the conditional variance. Yes, for the conditional variance, HT is defined in the following formula, where HT is equal again to omega plus alpha 1 r squared in time t minus 1 plus beta 1 h in time t minus 1. Yeah? So this is again our well-known formula for conditional variance. This can be written as, and then we have again HT equal to omega divided by 1 minus beta 1. Yes, omega divided by 1 minus beta 1 plus alpha 1 logarithm squared in time t minus 1 plus alpha 1 beta 1 logarithm squared in time t minus 1 plus alpha 1 beta 1 squared logarithm squared in time t minus 3 plus etc. This series can continue, yes, from which it follows that HT is a weighted sum of past squared log returns. Yes, HT is a weighted sum of past squared log returns. So this is the situation for HT, the conditional variance, which can be rewritten to this formula. Yes, and we are speaking about our infinity model. Yes, and de-identification. As you can see from the previous slide, that there is dot that can continue. Yes, and we would like to know, yes, because it's not possible to reach p equal to infinity. Yes, but we can reach p equal to 10, 11, 12. Yes, some number. Yes. So identifying of arc or GARC model in practice. Plot the series to spot periods of increased variation through the series. Yes, and look at the autocorrelation function and partial autocorrelation function of yt and yt squared. So what is it now? Yt and yt squared. Empirical data of the analyzed time series, yes, and squared values of this data set in time t. So empirical values and the squared empirical values, yes. Squared empirical values are non-negative every time, yes. Empirical values, yt, can be positive or negative or equal to 0, yes. Okay, so plot the series to spot periods of increased variation through the series. Look at the autocorrelation and partial autocorrelation function of empirical data and squared empirical data. If yt empirical data appears to be white noise, and appears to be auto-regressive model of the first order, then an arc 1 model for the variance is suggested. Yes? So, if yt appears to be white noise, and appears to be AR1, then on arc 1 model for the variance is suggested. Yes? If the partial autocorrelation function of squared empirical values, yt squared, suggests autoregressive process of order m, yes, for example, then Rm may work. Yes, so this is again the rule. GAR models may be suggested by an ARMA type. Look to the autocorrelation function and the partial autocorrelation function of yt squared. Yes, so again, generalized autoregressive conditional heteroscedasticity models may be suggested. Yes, may be suggested by an ARMA type. Look to the autocorrelation function and partial autocorrelation function of squared values of our dependent variable. In practice, real models do not work as nicely as they did for the simulated examples. Yes, we simulated a lot of time series, yes, for the purposes of our education, yes, and for our illustration in Excel and use, because it's very difficult to find nice time series where it's easy for students, yes, to find the nice model. Yes, it's very, very complicated. So in practice, real models don't work as nicely as they did for the simulated examples. You might have to experiment with various arc and GAR structures. Yes, so there exists procedures with some automatic selection of orders, automatic selection of locks, automatic selections of models, yes, where for you is generated a table with a lot of models, with information criteria, yes, and with other diagnostics, and according to this table, you can check it and you can see that, okay, we will select this type of model because then you can see the minimum values of information criteria or the stars which can indicate the significance of the model, etc. Yes, so this is quite important that you might have to experiment with various arc and GAR structures. Okay, so this is the end of our today 9th seminar. Yes, we again talked about volatility models. You could see that it's not easy like before, yes, and I hope that it was clear and you know how to do this in practice. Not only on simulated data, yes, because we mostly use the simulated data because you know that it's difficult to find, yes, in the real data sets, yes, the nice time series where it's possible to model, to find nice arc or GARC model, yes, but I hope that you know this process, yes, and for example in your future job or in for example your absolvent thesis, yes, the final absolvent thesis, etc. You will be able to use these processes and find some appropriate model on the real time series. So that's all for today. I hope that everything was clear, I hope. I wish you a nice rest of the day, and I hope that I will see you next week on seminar number 10. So that's all, and have a nice day. Bye bye.